In this video, we're going to take a look at Lagrange polynomials again, but this time we're going to talk about how do we recursively evaluate those. And so to do that, let's first talk about a new definition, a new notational kind of thing. So rather than merely recursively evaluating higher degree polynomials, we can recursively develop the polynomials themselves. So let's say we have this function that's defined at these points, x0, x1, up through xn, and we have this set of integers. We have k distinct integers. Really, we're thinking about indices for these points right here, so that those indices are between 0 and n. They're going to be values that live in there. The Lagrange polynomial that agrees at just some subset of those points is denoted P with a subscript M1, comma M2, M3, up through MK. So let's think about what that means for a minute. Let's look at a quick example of this. So let's let x0 be 1, x1 is 2, x2 is 3, x3 is 4, and x4 is 6. The function that we're going to look to try to find the Lagrange polynomial is e to the x, and we are going to determine the interpolating polynomial p1, 2, 4 of x. And so p1, 2, 4 of x. What does that mean? That means that we are going to use the nodes with subscripts of 1, 2, and 4. So those are not the x value, the y values. Those are the subscripts of the x values, right? So the subscripts of the x values, not the x values themselves. And so what this is going to look like is L1 of x1, not of x1, but of x, times f of x1, plus L2 of x times f of x2, plus L4 of x times f of x4. And in this particular example, the way that we find L1 of x, we're going to take the other nodes that we're using, right? And so we're using x2 and x4. We're going to subtract those from x, right? So we have x minus the x2 node, which is 3, times x minus the x4 node, which is 6, over the x1 node, which is 2, minus 3, and 2 minus 6, times the function value at x1. So the function value at 2 is e squared. And then we do the same thing for L2. We have x minus 2 and x minus 6 over 3 minus 2 times 3 minus 6. Our function value there is e cubed. And then L4 is going to be x minus 2, x minus 3 over 6 minus 2, 6 minus 3, e to the 6th, right? So here, when we have these subscripts here, this says we are using node x1 and x2 and x4, sorry. And so those are the nodes we're using, x1, x2, and x4. And when we are using looking specifically at x1, we are omitting x1, and we have x minus x2 and x4. then we take x1 minus x2 and x4. And we roll through that. So that polynomial, we can calculate it. The polynomial found in this way, it is unique. So when you look at the polynomial, it is what it is. However, the representation of that polynomial is not unique. And so what we can do is we can try to find out a different way to represent this polynomial. And so what our goal is going to be is we are going to try to represent our polynomial Pn of x in such a way that we can build it out from our old polynomial, right? So we have the previous polynomial, and then we're going to somehow tack on a new node. But it's not just multiplying by this. We would also need to add some other business here. And so we're going to think about, what is this other stuff here? How do we build that out? And so we will talk about that in the next section.